There's a planet orbiting a dim star 124 light-years from Earth. It is not a rock like Mars or a gas giant like Jupiter. It sits in a size category that does not exist anywhere in our own solar system, something between Earth and Neptune, a kind of world we have never been able to study up close. It sits at exactly the right distance from its star for liquid water to pool on or beneath its surface. And when the most powerful space telescope ever launched spent months analyzing the chemistry of its atmosphere, the data came back carrying the fingerprint of a molecule that everywhere we have ever looked on this planet is made by living things. That molecule is called dimethyl sulfide. On Earth, it is released primarily by microscopic marine life. Phytoplankton produce it in the ocean's surface layers as a byproduct of their biology. It drifts up into the atmosphere, and in sufficient quantities, it contributes to the smell of the sea. It is not a molecule that rocks produce. It is not a molecule that volcanoes release. Every source of it that scientists have identified on Earth traces back, directly or indirectly, to biological activity. Webb found it, or something that looks very much like it, in the air of a planet over 100 light-years away. Before you allow yourself to feel the full weight of that sentence, you need to understand exactly what kind of claim is actually being made here, because the scientists involved are being extremely precise about what the data does and does not show, and that precision is itself part of the story. The planet is called K2-18b. It was spotted in 2015 by the Kepler Space Telescope, identified through a method called the transit technique. Every time a planet crosses in front of its host star from Earth's point of view, it blocks a tiny fraction of that star's light. Kepler was designed to detect those dips, and it found thousands of them. K2-18b was one candidate among many, a point of light dimming slightly on a 33-day cycle, suggesting a planet completing one full orbit every 33 Earth days. The star it orbits is a red dwarf, significantly smaller and cooler than our Sun. That means its habitable zone, the orbital band where surface temperatures could allow liquid water, sits much closer in than ours does. K2-18b lands squarely inside that zone. For a while that was interesting, but not remarkable. Habitable zone planets around red dwarfs had been found before. What made this one stand out was what happened when scientists looked more carefully at its size. With a radius 2.6 times Earth's and a mass 8.6 times greater, K2-18b belongs to a class of worlds called sub-Neptunes. These are extraordinarily common across the galaxy. In fact, the most statistically typical planet in the Milky Way appears to be something in this size range. And yet, our solar system has none of them. We have rocky worlds topping out at Earth's size, and then a gap, and then ice giants beginning at Uranus. Nothing in between. Which means everything we think we know about how sub-Neptunes work is theoretical, built from telescope data, rather than from any probe that has ever visited one. One of the theories that has grown up around the larger members of this size class is the concept of a Hycean world. Hydrogen and ocean compressed into one word. The idea is that a sub-Neptune of roughly K2-18b's dimensions could sustain a thick atmosphere made mostly of hydrogen, sitting above a vast global ocean of liquid water. No rocky surface beneath the waves, just water deepening under pressure for thousands of kilometers. The atmospheric chemistry you would expect above such a world, if the models are right, would include methane and carbon dioxide, relatively little ammonia, because ammonia dissolves into liquid water and gets scrubbed from the air, and possibly biological gases, if anything, lived in that ocean. When Webb turned its instruments toward K2-18b for the first time in 2023, the atmosphere delivered methane at a confidence level of 5 sigma, a threshold so statistically stringent it is used to declare discoveries in particle physics. Carbon dioxide appeared at 3 sigma, strong but not yet at the level considered definitive. Ammonia was notably absent. The chemical picture lined up with the Hycean model, and buried in the same data, at much lower confidence, there was a faint signal consistent with dimethyl sulfide. The team that published this finding was led by Niku Madhusudan at the University of Cambridge. They were not reckless about how they described it. They noted the tentative signal. They listed the caveats. They were explicit that they were not claiming a confirmed detection of a biosignature. The paper, nonetheless, lit a fire under the scientific community because even a tentative signal of a biologically produced molecule on a habitable zone ocean world was the kind of result that demanded immediate scrutiny. That scrutiny came quickly and from multiple directions. The core problem with the dimethyl sulfide signal is a technical one. The wavelengths at which this molecule leaves its mark in an atmosphere overlap significantly with those of methane, ethylene, and a handful of other common molecules that have nothing to do with biology. When you try to fit a model to atmospheric spectra, you are essentially adjusting the mix of gases in your model until the predicted spectrum matches what the telescope actually recorded. The trouble is that several different combinations of ordinary gases can produce spectra that look nearly identical to the spectrum U. would get from a small amount of dimethyl sulfide. One group of researchers demonstrated that replacing the dimethyl sulfide in the model with ethylene, a simple hydrocarbon produced by geological and chemical processes with no biological requirement whatsoever, produced an equally good match to the data. The signal did not require life. It was consistent with life. Now, those are two very different things. That was the state of play heading into 2025. A planet that passed every structural and chemical test a habitable world could be asked to pass, sitting above a faint and ambiguous signal that kept refusing to go away, but also kept refusing to become unambiguous. In April 2025, the Cambridge team published again. This time, they had used Webb's mid-infrared instrument, a completely separate piece of hardware observing at wavelengths between approximately 6 and 12 micrometers. There was no overlap with the earlier observations in terms of the wavelength range covered. This was not the same data looked at differently. It was new data gathered by a different instrument sensitive to different parts of the spectrum, and it was gathered for the specific purpose of testing whether the earlier signal would show up again from a completely independent measurement. Dimethyl sulfide and its close chemical relative dimethyl disulfide appeared again at roughly 3 sigma confidence. The team reported this as the strongest evidence to date of biological activity beyond our solar system, and then immediately walked that statement into a room full of caveats, stressing that non-biological explanations had not been eliminated, that the signal had not reached the 5 sigma threshold required for a confirmed discovery, and that additional observations using multiple instruments across a broader range of wavelengths were essential before any firmer conclusions could be drawn. Other research groups took the new data and reached somewhat different conclusions. A NASA-led reanalysis, combining all available Webb observations of K2-18b, placed the dimethyl sulfide signal at 2.7 sigma, slightly below what the Cambridge team had reported and well beneath the detection threshold the field requires. A separate independent analysis confirmed methane and carbon dioxide with high confidence, but found no statistically significant evidence for the sulfur molecules in particular. A third group showed that the spectral features attributed to dimethyl sulfide set close enough to those of other molecules that the choice of how to process the raw telescope data before analysis could make the signal appear or partially disappear, depending on which approach was used. None of this resolved the question. What it did was illustrate precisely how difficult the question is to answer. Detecting a trace gas in the atmosphere of a world 124 light-years away, through the filter of all the other molecules sitting alongside it, through the noise floor of even the most sensitive telescope humanity has ever placed in orbit, is a problem that sits right at the boundary of what is currently possible. Webb can ask the question. It cannot yet answer it conclusively. A survey of astrobiologists conducted in 2026 found that fewer than 7% believed the existing evidence justified claiming Webb's had found signs of life on K2-18b. The scientific community is not convinced. It is interested. There is an important difference between those two states, and the researchers involved understand it well. What happens next depends on telescope time and patience, both of which are finite. Webb is the only instrument currently capable of this kind of atmospheric characterization at K2-18b's distance. Pushing the dimethyl sulfide detection from 3 sigma to 5 sigma, if the signal is genuinely there, will require substantially more observing time on a single target that is competing for those hours against black holes and distant galaxies and every other phenomenon the telescope was designed to study. The process will take years. The answer may come back stronger. It may come back weaker. It may not come back at all if the signal turns out to dissolve under the weight of more data pointing in a different direction. This is how science actually works. Not with a single dramatic announcement that settles everything at once, but with a slow, contested, methodical accumulation of evidence that either builds into a case strong enough to stand on or quietly falls apart under examination. The K2-18b story is in the middle of that process right now, at the stage where the signal is real enough to spend resources investigating and uncertain enough that no one with a reputation to protect is claiming they know what it means. What is not in doubt is what the planet is. A world more than 8 times Earth's mass sitting inside the habitable zone of its star, with an atmosphere whose chemistry points toward a deep global ocean, carrying confirmed methane and carbon dioxide and a persistent, stubborn signal of something that might be produced by living things swimming somewhere beneath those clouds. We cannot visit it. No instrument we currently have or are planning to build will ever get there within any time frame that matters to anyone alive today. Everything we will ever know about what lives in that ocean, if anything does, will have to come through the light that filters through its atmosphere and travels for 124 years before landing in the mirrors of a telescope we put in orbit around the sun. That is the picture we are working with. Not a confirmed detection, not a dismissal. A planet that, every time scientists look at it more carefully, looks a little more like a place worth watching. and a molecule in its air that, if it is really there, would be the most significant measurement in the history of our civilization. Whether it is really there is something we do not yet know. Thanks for watching, and I'll see you in the next one.